Okay, welcome to this video. I think we're ready to go. What I'd like to have a chat to you about today is looking at downforce and some formulas that you can use to calculate downforce, and also having a look at some computational fluid dynamics. And we're really looking on downforce and friction forces and how they work together. So the first thing that we have here is pressure equals force over area. And what pressure is, it is in essentially a force, but it acts normally to a surface that's perpendicular to a surface. So a pressure that you could think about is pressure in tyres when you pump your tyres up in your car or your push bike. And it's measured in pascals, and force is in newtons, and area is in meters squared. To change this formula around, we have force equals pressure times area. And we're really interested in that force because we want to work out what the drag force is, and we want to work out what the down force is. So the next thing that we can actually look at with pressure is we can determine pressure of an object traveling at a particular velocity, or we have air traveling at a certain velocity hitting something. So you can think of an example that you had a sign beside the road. Let's do this. So we have a sign that's beside a road, and we have air hitting it at a certain velocity, and we want to work out what the pressure is on that surface area. And we can do that with this formula, which is pressure equals half the air density times velocity squared. So what is the air density? Well, I'm glad you asked. At sea level, it's 1.225 kilograms per meters cubed. So that's what we're going to be using for the density of air. And we can represent that in this formula, which is P equals half density of air velocity squared. So what we're going to do is take that pressure formula and pop it in here for the pressure in this formula. So now force equals half the density of air velocity squared, all in brackets, times area. We don't need the brackets, but it just helps you understand it a little more. So what I've done here in black, as you can see around the outside, is this is my wing. It's my wing that's going to be creating downforce on my model race car. And it's 70 by 150. And it's at a 10-degree angle. And what we have here is the car's traveling at 5 meters per second. So the air that's going to be hitting this from this direction is going to only be, the amount of air is if I project out at right angles or horizontally, this is the amount of air that's going to be hitting the wing. And we can work out what that area is, and I've got it over here. And if it's 70 here, then it's going to be 70 sine 10 is going to be the height here, and the length is going to be 150 from here to here. And this is what we call the drag surface area, because this is the amount of air that's hitting the wing. And we can calculate the drag by using that formula again. And that's half density of air times velocity squared by 150 millimeters in meters, and 70 sine 10, or 70 millimeters times 10 in meters. And we've worked out that the amount of drag that we have from a wing, which is 150 by 70 at 10 degrees, is going to be 0.0279 newtons. That's going to be the drag force. So from there, what we're going to be able to do is work out what the down force is. To do that, we're going to be using a space diagram. Here's my wing. Here's the drag force coming across. Here's the down force acting down. And what we have is this normal force. Now, the normal force is acting at 90 degrees to the surface area, 90 degrees. And that is the force acting downwards. on that wing in this direction. We need to take that into account. So then, if we just go over to the free body diagram, we take out the wing itself. We have a normal force acting down at 10 degrees to the wing, the drag, and the downforce. So we're going to create a force diagram out of it. See, the downforce acting down and the drag force, those two forces make up the normal force. So the resultant of these two forces is the normal force. Now we have the drag force here, which is 0.0279. So we should be able to work out the down force with a bit of trigonometry. And that's what we've got here. So the down force equals the tangent, tan theta equals opposite over adjacent. So it's tan 80, the down force over the drag force. And this is what we've got with our final calculation. We've got the down force equals 0.158 newtons. That's the amount that we have. So if we sort of slip on down here with our car, we can actually show what our downforce is. So how is that going to work for us? Well, we can actually sort of calculate some friction forces. And what we normally have when something's flat on the ground is we have the weight acting down of an object. We have the normal reaction acting up, which is the pushing force, the equal and opposite to the weight. And then we have the friction force acting as well. Then we have another force sort of rotating or pulling this that the friction force is going to resist. All right, so we have two different types of friction. And it's represented by a thing called a coefficient of friction. And it's represented by this funny little U. And we've got two different types of friction. We have a static friction and we have a kinetic friction. Now, the kinetic friction is a slipperier type of friction. And now when a car loses its traction, it goes into kinetic friction. That means it's sliding or drifting and it's slippery. If something is not, if it's not, the wheels aren't spinning or it's not skidding around a corner, it's still in static friction and it's not slipping. And that's what we really want to obtain. We want to obtain static friction. So normally we could work out what our static friction is or our friction force is by calculating what the coefficient of friction is divided by the normal reaction. Now, where downforce is handy because that normal reaction is going to be increased once we add our weight, once we have our weight, which is normally our normal reaction, but we have our weight plus our downforce. The coefficient of friction is always going to stay the same, but adding that extra downforce is going to give us a higher amount of static friction, which is going to hold the car to the ground. So how do we work out the friction force of our car? Well, what we can do is to work that out, is get a Newton spring, put it on the back of the car, on the wheel, and just start pulling it until it moves. And then we can actually look at that Newton spring and see what force was required for it to start slipping just before it slips. Now, for this sake, I've given an arbitrary friction force of 1 Newton. So, and I've given an arbitrary weight of the car of 2 Newtons. So what I can do then is just work out what the coefficient of static friction is. The friction force over the normal reaction, 1 over 2. So we have this unitless number, which is 0.5. So therefore, the friction force once we add the downforce increases substantially. So we have our normal weight plus the downforce, and we can determine out what our new friction force is by adding this downforce in. And that's what I've done here. So how is that going to help us with our friction force? Find out what our friction force is? Well, by using this formula, which is the centripetal forces, what we can actually do is determine what the velocity will be for this amount of friction force in the car. And I've said it was moving at 5 meters per second, but let's see if we can actually get it to stick at 5 meters per second with this size wing and the amount of downforce. Now we have here that R is the radius, V is the velocity, M is the mass, and Fc is the friction force. So what we have is the car going around at a certain velocity and radius, and the friction force is the centripetal force pushing in. And here's an example of that with the power anchor. So we've got the power anchor in the center. We've got the radius, and that's the tether attached to the car. And what we have is a friction force sort of pushing this car out. Now, there might also be a moment force here, which I haven't calculated for. And it may be negligible or it may be important. I'm not quite sure. It's for you to work out and to do some additional calculations about. So if I want to work out, if I know what the friction force is, which we just calculated above, I can work out what the velocity is or should be. And it's a mathematical velocity in a sense that it's theoretical velocity. In real life, you know, lots of things happen, but it's just a theoretical velocity. So I've changed the formula around. Velocity equals square root of radius over friction force over mass, and mass never changes. So what we have is the radius of the power anchor is 2, the friction force is 1.079, and the mass is 2, which was the weight, divided by 9.8, and that's what we've got. So we plug that all into the formula, and we end up with a velocity of 3.25. So really, with the size of the wing that we've got, it's not actually able to do 5 meters per second, but you can change those formulas around to play around with velocity and theoretical speeds that things can up to. To obtain the velocity of 5 meters per second, the car will be required to increase the downforce. Consider using this formula instead. All right, well, what's another way forward? Well, we can also use computational fluid dynamics to determine the downforce of a wing. So we calculated the downforce of the wing to be here, to be 0.158. So what I've done is I've used Autodesk Computational Fluid Dynamics, the education version. And what I've done is I put a wing in exactly the same dimensions as the wing up here. And what I have then determined to do was to find out what the downforce is. And what I have here is the downforce, which is 0.1508 whatever. So it's pretty close, right? So this is a computer-generated downforce modeling, and it's pretty close. So if you wanted to, if you didn't want to do all these calculations up here, these initial calculations that we've got pretty much to here, you could just play around with, just using computational fluid dynamics to do that. And what we also have here is the, here it's the y-axis. So this should be the drag, which is 0.068. But if we go up here, what do we get for, so it's a bit different in the drag force. And that's because every wing has a thing called a coefficient of lift. And the coefficient of lift really has to do with how an object moves through the air. And there's this thing called the Coanda effect. And the Coanda effect is that a fluid, and air can be seen as a fluid, will stick to the surface of a object as it runs through. And I've just got a couple of videos to which I've just given an example of that, of a ball with water rolling over it. And also I've got a wing that's been 3D printed that's been used for downforce before, and you can see how that's sticking to the surface. So you need to take that into consideration. You need to take that into consideration. And computational fluid dynamics, if you're designing a particular wing design, will help you to find out what that is. And you can search for formulas for downforce, and it will have the coefficient of lift or the coefficient of downforce that you can calculate. So I hope that's made sense to you. I'm going to make some more videos for the computational fluid dynamics. I've got some old ones there, which you can refer to. But watch the new ones first, where I'm just going to take a wing and put it in and do exactly what I've done there, because it has, obviously, as Autodesk upgrade to different versions, things change. So keep your eye out for those. Hopefully we'll be doing those before the end of today. So that's the end of the video. Hope you enjoyed it.